Division is kind of problematic though, right? The problem with division is, well, let's look at an example. And the first problem you get with division is this one.
Have to rationalize it or something like that?
Why do you think that?
The book says it. Yeah.
Because the book says it.
I read it in the textbook.
Right, okay. Yeah, so if you think back to your numbers which are real, we had an operation or a skill that we taught called rationalizing the denominator. And the reason why we did that was we generally like to express things with a rational denominator. It just makes things a bit nicer, makes things easier to work with. We have a similar kind of skill over here. But hang on, if we're thinking about rational numbers, I don't know, it doesn't really work when we're working with like complex numbers, they're separate kind of things, right? Sorry?
I is fake.
I is fake, right? I is lateral units, not imaginary, right?
What do you do with the conjugate? Is that what it's called?
Yeah, so if you think back to your rationalizing denominators, if you get an example like...
It was the end of the big greedy bit, and I was getting excited about it. And I didn't have any questions on that at the time, so...
Okay, so if we had something like this, and we were trying to rationalize its denominator, right, what would we multiply by?
0, 15 plus 2.
Okay, right. Right, and what does that actually achieve? Well, when you multiply this out, you're going to get something with a rational denominator, as we expected. Like 11, right? So a bit messy, but yeah, okay. So the goal and the thing that it achieves is being able to write this with a rational denominator. When we think about division of complex numbers, though, thinking about what term we have to multiply by allows us to define division. Because remember, what does a complex number have to be defined by? It has to be defined by expressing a term as a plus bi, expressing a number as a plus bi. And again, that's not immediately clear here because I can't really see what is a or what's b, right? I don't have some value that's by itself. I don't have a single value that's multiplied by I. It's not very clear at this point. This value that we're multiplying by, we call that the conjugate. And that's actually a name that we give to real numbers as well, but we also give it to complex numbers. To define the conjugate, we're essentially changing the sign of the imaginary component. So over here, we would just say, change the minus to a plus, change the plus to a minus. But with complex numbers, we're specifically looking at the imaginary component. So when we're looking at the conjugate. Sometimes I'll also refer to that as z bar with the number on top. So if you have z is equal to x plus iy, then the conjugate will be x minus yi. That's our definition of the conjugate. And we'll look at that formula more in next lesson. But what that allows us to do is to solve problems like this. It allows us to define division of complex numbers, right? So in order to express this in the form a plus bi, well, what I can do is I can multiply by my conjugate. Exactly right. And so you can see how we're incorporating all of these together now, right? When we want to define division, we need to be able to multiply by the conjugate on the numerator and the denominator. And then what do we have in the numerator? Well, we've actually got our definition of multiplication of complex numbers, which is our expansions, right? What are we going to get on the denominator now?
16. Oh, wait, no, minus 17.
We'll get 16.
Oh, no, minus 16 minus 1, so...
So yeah, just be careful how quickly you do this, because let's write it out like this first. 4 plus I, 4 minus I. And you're used to seeing the difference of two squares when we're talking about real numbers, right? Over here, well, what's going to happen? Well, right, it adds 1. And in fact, this is called the sum of squares in complex numbers, because when you think about it, we have a negative here, but we're getting I squared. And we know I squared is negative 1, so we're actually always going to be summing them. That's an identity that we can use, the sum of two squares, yeah. So, yeah, it's just tweaked slightly because of the fact that we use our imaginary units. So what I can recognize is that this denominator is always going to become, I think it always, well, depending on the coefficients, it will always become a real number at least, right? So when we're doing that, we're going to get 16 minus I squared, which I'll fill in later, and we can do this expansion as well. We'll get 12 minus 3i minus 16i plus 4i squared. Yeah?
Down 17.
Yeah, and then this guy, 16 minus I squared, that's just going to become 17 in the denominator. Maybe I'll do it over here, so it's a bit more. So 17, and what are we getting in the numerator here?
So minus 4, 8 minus 3i plus, wait, 8 minus 3i, 8 plus 3i, English, 8 plus 3i.
Yeah, so we've got 12, and then what plus 4i squared we can think of as minus 4, right? Because I squared is negative 1. So we get 12 minus 4, which is 8, and we've got minus 3i. That's meant to be a minus, hey? Minus 16i, which becomes minus 19i. Okay.
Okay, so then what do we do?
Well, here's the thing. How did I define what a complex number was?
Oh, I thought that was a plus 6, not a 6 minus 6.
That's all right. What was our definition of a complex number? Our definition was z is equal to, z is equal to x plus yi, yeah? Is it clear what x and y are right now?
Well, yeah, would it be 8 over 17 minus 19 over 17?
Exactly right. You can split these guys up so that it's clear that you have those two clear values, right? 8 over 17 minus 19 over 17i.
Is that literally it?
Yep. So those are our values. Get that down for me.